So last time, we were looking at the scattering of a Gaussian wave packet from a step potential. So we have a potential, which is like a step, and we had quite a spread out Gaussian wave packet because its momentum was pretty well defined. Coming, and its average energy was greater than the height of the potential. And we expected on physical grounds that after the wavefront, after the wave packet hits the potential, it'll get reflected, and there would be a reflected wave packet, and there would be a transmitted wave packet. Okay, so our strategy for that was that we expressed the initial wave packet as a linear combination. So our strategy was that the initial wave packet we expressed it, initial wave packet, as a linear combination of the energy eigenstates, right? And then once we have the energy eigenstate, we can just evolve the wave packet in time by simply multiplying the eigenstates or the eigenstate, say with energy E by e to the power minus I by h bar E of t, right? So this is really wonderful because what we're doing here is we are using the linearity of quantum mechanics to evolve our system. But in practical terms, we had 3 steps. And step number 1 was we solved for the energy eigen, we solved for psi e of x at time t. Okay, this is at time t equals to 0, sorry. And then we expressed in the last class the initial wave packet in terms of psi e of x. Okay, and then what we need to do today is to, from psi of x of t, which is the evolved wave packet as time t goes to infinity, we want to identify what is the reflected part and the transmitted part, because as time goes, more as t goes to infinity, they should separate, right? There shouldn't be any overlap between the two. And from those compute, the reflection coefficient and the transmission coefficient. Okay, so is the general philosophy clear?
Sir, could there be any situation where there isn't a linear combination?
Well, no, I mean, because the Schrodinger wave equation is a linear wave equation. That's why we use heavily on the linearity. There are models of quantum mechanics where the wave equation is not linear. So the Schrodinger equation has some nonlinear terms. And those are used to kind of try to explain somehow physically the collapse hypothesis, but no real evidence has actually been found of nonlinearity in quantum mechanics.
Oh, okay.
Okay.
Yeah.
Good. All right. So at the end of step 1, we found that our wave energy eigenstate psi of E of x, we expressed it also in terms of k. So we replaced that by psi of k1 of x, where k1 was the wave number of the region 1, and we found that psi of k1 of x was the normalization constant a, and then we had exponential of I k1x plus b by a, exponential of minus I k1x. So this was the part of the energy eigenstate which was on the negative x-axis. So that gets multiplied by theta of minus x, where theta is the Heaviside step function. And then we also have another one on the positive side of the x-axis, and that is given by exponential c over exponential e to the power I. And here we had k2. And k2 can be expressed in terms of k1 in terms of k squared minus 2m v naught by h squared, the whole thing square root under square root x. And this thing is multiplied by theta of x. Okay, so this was at the end of step 1. Okay. And at the end of step 2, we found, so what was step 2? Step 2 was expressing the initial wave function as a linear combination of this guy, right? So this was at the end of step 1. And at step 2, we wanted to find psi of I, the initial wave function, as a linear combination of this guy. So we have to integrate over k1, and these are the coefficient of linear combination that we have to find out. Here psi of k1 of x. And we know that this is given by the fact that, these guys form an orthonormal set. We know that A of k1 would be given by the inner product between psi of k1 and psi of I. Okay? So, right. Now, this integral involves an integral over x. So if I look at that integral, and what I find is we can factor out A. A is a function of k, of course, but it's not a function of x. So we found that we had terms such as so this comes from k1 e to the power minus I k1x. So here what we're doing, we are factoring out the a, which we did before, and the sign here has changed. If you look at here the sign was plus, here the sign is minus because this is on the left side of the inner product, so we have to complex conjugate it inside the integral. Okay, so, and then we have b over a, and this has to be complex conjugated as well. And then we have e to the power I k1x. The sign has changed here. And theta is a real function, so that doesn't change. And then psi I of x is this guy. Okay, and all of this we are So the integration sign should be actually outside the square bracket. Oh, yeah, this integration sign should be outside. And there's a dx, okay? So this is the integration inner product with this part. And now we have to do the inner product with this part. And that is, again, plus integral over from minus infinity to plus infinity. Here C over A is complex conjugated, e to the power minus I k2, which is of course a function of k1 times x, and then theta of x psi I of x d of x. Okay, so this was A of k1. And then what we did is that we said that this integral is actually not very hard to evaluate. So the initial wave function, psi I, this guy, has only support on the negative side of the x-axis, right? Where, and in that negative part of the x-axis, what happens is that this thing is 0, right? So that means that this last integral is going to be 0. Because where this is non-zero, this is 0, and vice versa. Okay? So, and the second term, like this term, now this thing, when you multiply it, what it does is that it has momentum modes which are all moving to the right. But this is the complex conjugate of the momentum mode which is moving to the left. Therefore, the inner product between these two things, and the integral only cares is only non-zero, where this is non-zero. So we don't have to take this into account. This is just 1. Because this is because where this is 0, this is also 0, right? So where the integral matters, this thing is 1. So the inner product between this guy and this guy by momentum orthogonality or momentum eigenstate is also 0. So this thing, second term doesn't contribute. So as a result, we just have one term. And in that term, theta is just 1. And then we basically have over there just a Gaussian integral. And if you do this integral, then we have A of k1. So it's a complex Gaussian integral, right? Because this is a Gaussian and this is multiplying some k1 factor. So if I do this integral, then it's, now you have to do these things, right? So I actually did this painfully, but we get e to the power I, k1a, and e to the power minus k minus k naught squared delta squared by 2. Okay, so this is end of step 2. Okay, so now we are going to do step 3. So any questions so far?
I have one question. So
yeah.
Could we have taken the inner product the other way around?
Yes.
I'm not.
Yes,
okay.
But then you would have gotten a star. You would have gotten a star. Okay.
How do we know which one is star and which one is not star? I'm kind of confused about that.
Right. So it's from the definition. If I so I define that psi of I, right, of x, that's given by, that's how A is defined, right? A is defined through this equation. Right? Is that clear?
Yeah.
Yeah. And then we have we are going to do psi of k1, psi of I. So because this guy is on the left side, that's why A is coming from this guy, right?
I see. Okay.
And so if I write this out, what I will get is that we'll get an integral over, say, if I write this out, d of k1 prime, and this thing is psi of k1, and this thing would be A of k1 prime, right? And here we will get psi of k1 prime, right? Is that clear? So,
Oh, yeah, I got it.
so now we can
Yeah.
bring this out. Let me just finish this for everyone. So dk1, and here we have delta of k1 minus k1 prime, and then using the orthogonality, we get A of k1. But if you take its complex conjugate, if you calculate this thing, psi I of psi of k1, then you would have gotten A star of k1, okay? All right, any more questions?